Today we are going to start with the new topic of thick shells. What is this thick shells? As we have earlier done in the thin cylinders, that when the values of your T by D ratio was less than 1 by 20, we have considered that as a thin shells. Now, in the thick cylinders, that must be defined if the T by D ratio is greater than 1 by 20, we will consider under the thick shells. Second assumption we have made in the thin shells, what is the differentiation between both of them? One is the T by D ratio, and second one is we have neglected the radial stress in that case, if you remember. So now we will be considering the radial stress in the case of thick shells. Next thing is that in the thick shells, we will be circumferential stress will be changing throughout the thick shells. Earlier we were having the similar values, now it will be changing. So the variation of the radial stress and the circumferential stress can be calculated through the Lamy's theorem. What is this Lamy theorem? We will go through the definition and derivation of that. In the Lamy theorem, we are having few assumptions that we need to weigh out before we do the derivation. First is that if we introduce the internal pressure fluid inside the thick shell through the internal diameter, at that time there will be no change in the external shape of the thick cylinder. That means if there will be any change due to that pressure, that will be elastic. First, there will be no change in the deformation of the material. Material will be not be changed. Second will be, if there will be a change, it will be elastic. And third one is that we are considering the material of thick shell to be homogeneous and isotropic. These three assumptions are necessary for starting the Lamy's equation. Now, let us come to a thick shell. This is a thick shell, say. We know that the internal side allows the pressure to flow. Vinay, you were asking the question about the diagram. This is the internal radius, that is R1. We have taken internal radius of thick cylinder. This is R2, that is the outer radius of the cylinder. Fluid will be flowed inside the R1. The pressure of the fluid is defined as P1, pressure of the inner surface. There will be a resisting force from the outside thick shell due to the wall, that is called as pressure on the outer surface. This is P2, because the internal will allow to burst the thick shell, and the thickness will allow to compress the thick shell. So that will be the P2 force. Now, for our calculation, we know that we have to take circumferential stress and the radial stress. The radial stress will be acting along the radius. This is R1, that is radial stress. This is R2 acting along the radius. Okay. Next will be your circumferential stress. For the thick shell, along the circumference, what is happening? That there is we need to calculate. We will be calculating the value for the your thick cylinder for the radial and the circumferential stress. Now let us assume a small section on the surface of the thick shell on the circumferential face. Now this will be your circumferential stress along the circumference. Clear by the name. And on this surface you are having a small width, that is dr, the width, and on this surface you are also having the value of the radial stress, that is stress r plus dr. So now on this surface I have taken three values. First is the thickness is dr, the value of radial stress is stress r plus dr, and circumferential stress will be same throughout the circumference. Whether I have taken the section, it will not convert into stress C plus D stresses. No, it will not happen. It will only happen in the case of radial stress. Let us come to the derivation. Now, in the case of derivation, you have to take the bursting force. The bursting force from inside, that is the radial stress into area, minus this assumption which you have taken, the small thickness, that is a hindrance in bursting of the force. So we will take in negative. Stress R, 2R into L minus stress R plus dr, which is the stress value for the small section which we have assumed, into the length of the section. We are taking the area, R plus dr into area. Why we have taken twice? Because it is the thickness, so we will be taking as twice to include the whole the section. Okay, now this is the quantity. On solving this quantity, we get this relationship, minus 2L stress R plus dr plus R into dr. Okay, now this is the bursting force which was coming from inside of the your cylinder. Now we will be taking the resisting force which will be coming from the outside due to the thick shell. Now resisting force will be along the circumference, because circumference is providing the resisting force. 2 stress C into L into dr, same. Now we will be again now taking the small section also in consideration. Now you must note that during the bursting force, this small section was acting in opposite direction. Bursting was from this side and this section was causing resistance. So we have taken in the negative. Now in the case of resisting force, we will take positive. Why? Because they both are acting in the same direction. Both are circumferential. It is acting along the circumference and one stress is due to stress C. So that means 2 into stress C and dr plus, we have taken on the other side, we have taken negative, 2L into stress R dr plus R dr. Okay. So now equating the equation of bursting force, because we have taken the section as homogeneous and isotropic, so we will taken this as both as bursting equal to the resisting force. Now when we equate these two terms, we get a relationship between stress C and stress R. Okay. Now let us come to the radial stress with another relationship. With the radial stress, we know the stress is equal to force per unit area. So force is the internal pressure P1 and your area will be pi r square. Your force will be pressure into area. Now stress is force per unit area. Area will be taken off your thick cylinder, that is pi r2 minus r1 square. But why we have taken only r1? Because fluid was flowing from inside. Okay, so we are considering the force due to the fluid acting longitudinally. So that is pi r1 square into P1. Area is of the whole thick shell, that is pi of r2 square minus r1 square. So we get the value of longitudinal stress. Now we have now three terms: circumferential stress, longitudinal stress and radial stress. Let us put that values into the longitudinal strain. Longitudinal strain include this relationship we have already done in the thick cylinders. We just put the values of stress E and stress R. We will be neglecting stress L, Young's modulus E constant, and the Poisson ratio 1 by n. So we got this relationship: stress C minus stress R is equal to 2A. Now we have taken one new term, that the constant name is 2A. Now let us calculate the value of stress C from this equation, that is stress R plus 2A. We put this value into the equation number 3 here, stress C, which we have generated from equating the bursting force and resisting force. Now we take this value and on solving this, we get this relationship. This is simple solvation, nothing else. You integrate both sides and you come up with this term. When you come up with this term, there will be introduction. When you do integration, there will be the introduction of constant. So we have taken constant B. Cancelling log on both sides, we get a relationship: stress R is equal to B by R square minus A. Stress C is B by R square plus A. So this was all about Lamy's equation. Simply you have to derivate this relationship. Now I have already told you about these terms. Stress R plus dr is the external radial stress for the small section. Circumferential stress is stress we already discussed. So let us come through one numerical also. You have this relationship, stress R is B by R square minus A. Shubham, stress C is equal to B by R square plus A. Now, let us see one thing, that you are given with R1 and R2, that is the external dia and the internal dia of the thick shell is given to you. Pressure is given to you which is flowing inside the cylinder. So now, what we are going to do, we will write stress R is equal to B by this one, B by R square minus A. So you will be taking R1 and R2, two equations. Stress R is B by R2 square minus A. And second is for the circumferential stress. Similarly, you will calculate for the circumferential stress. You will get the values of B and A as unknown values. So you will simply find out the values of B and A and put into the another relationship to calculate the radial and circumferential stress. This is our desired output. So this question will come into 10 marks excluding numerical, the derivation part only. If the numerical will come, it has special 4 more cases we will discuss in the next classes. This was the basic, when fluid flows inside the cylinder and fluid that impacts on the walls of the thick cylinders. What happens at that time? We have generated two equations, that is for radial stress, circumferential stress. That is B by R square minus A for radial, B by R square plus A for the circumferential. So this was all about the thick cylinder. Now you just calculate